Okay, welcome to lecture here. Okay, we're going to get started here in just a second. So as usual, if you have questions, feel free to ask them down in the box and come on back here. There you go. And we're going to pick up here in chapter 9, hopefully get through most of it and perhaps get into chapter 10, which is also up there as well. Okay, so let's talk about, we're talking kind of about phases and phase changes and water and some of the properties of water. So I think this is where we left off. I think last time we finished up talking about boiling. So here we're going to talk about liquid and gas phases. So obviously as we go from the liquid phase to the gas phase, so as we go from liquid to gas, or gas back to liquid, each of those processes obviously have a name associated with it: evaporation, as we go from liquid to gas. And as we go from gas back to liquid, that is condensation. And in terms of energy, it does make a difference in terms of what is happening. And by the way, this transition does occur at the same temperature. So, for example, for something like water, that's 100 degrees Celsius. This transition occurs at its normal boiling point. And really, for example, for water at 100 degrees Celsius, you pretty much have both phases in equilibrium with each other. So you have basically liquid and gas really there together. Not until you get, again, a little bit above 100 degrees, for example, for water, that you kind of go into the gas phase. Not until a little below 100 degrees that you're back in the liquid phase. But dead on 100 degrees is essentially where this transition occurs. If we're going from liquid to gas, that's an endothermic process. Again, endothermic processes means in terms of energy, energy is absorbed. So if you think of sort of an easy example, if you heat up some liquid water, you need to put energy in by putting a fire underneath it. And obviously the heat from the fire will cause it to start to boil at its boiling point. And again, those liquid water molecules will gain enough energy basically to separate from each other and head off into the gas phase. Now, condensation is the opposite process. It's the process where we go back from gas to liquid, and that's an exothermic process. And an exothermic process, again, energy is released. So basically, in that process, you have the steam, if you will, in the case of water, basically flying around. So as it loses energy, those water molecules basically kind of collide with each other, and they no longer have enough energy to stay apart. So they sort of clump together, if you will, and kind of fall back into the liquid phase. Um, and that will be an exothermic process. In terms of endothermic and exothermic, I know we don't talk too much about energy in here, but delta H, which is the enthalpy or the heat of a reaction, is basically used a lot of times to represent either something being endothermic or exothermic. If you have a delta H value that is negative, it's exothermic. If you have a delta H value that's positive, it's endothermic. So sometimes with chemical reactions and so forth, they'll oftentimes just give you the delta H value. And from the actual sign of it, you can determine whether or not something is exothermic or endothermic. So as I mentioned, as the liquid molecules basically escape uh, the liquid phase, it takes a lot of energy to sort of do that. And the liquid water is sort of cooled because it takes a lot of those energy as they leave the liquid part of the water to go out into the gas phase. And as they finally enter, for example, into the gas phase, because it took so much energy to sort of break apart, they are moving typically slower than the air molecules that are out there already. And as a result, basically the air is cooled because it has a less net kinetic energy. So as we sort of talked about a little bit before, sort of, boiling is a cooling process in that sense, because it does take a certain amount of energy to get those guys out into the gas phase. Now, as water cools, the evaporation rate decreases, and you can contain. Oh, let's say that right. Or try that again. You can maintain the evaporation rate of water with contact with some type of warm surface, like your skin. And that's why, for example, we feel cold when we do have water on our skin. So if we went swimming and got out of the pool, or you get out of the shower and you have all those water molecules basically on your skin and your body is going to start to basically supply the heat and energy to start the process of evaporation, right? So you got your water molecules there on your hand. Your hand is going to supply the heat and energy to start that evaporation process of the water. And as it does, obviously, we start to feel cold as a result of that, again, because our body's giving away the heat to, say, water on your hand or whatever it may be. That's also why, right, we use the process of sweating to cool us down. When our body starts to sort of overheat, we start to sweat. Because we start to sweat, we get basically water on our body. The excess water sort of increases the rate of evaporation, which means it's going to increase the rate at which your body is going to give up some heat and energy, and thus you will feel cooler as you start to sweat, obviously, as you start to cool down. So, evaporation is actually a cooling process in that sense. So when we talk about the surface of a liquid like water, this sort of process is sort of constantly occurring. Um, and we sort of talked about a little bit when we were talking about evaporation when we have water. Again, at the surface of really any liquid, you got both phases sort of happening and both effects. You have some liquid molecules jumping out into the gas phase. You have some gas phase guys that are dropping back down into the liquid phase. Now, when we do get slower moving water molecules, like vapor molecules, they start to condense into the liquid phase. Hydrogen bonds are starting to be made and energy needs to be released. So, typically, when we make some type of bond, we are going to release energy. Again, a exothermic process. When we sort of break bonds, it's an endothermic process. Remember as well, hydrogen bonding is one of those intermolecular forces, the forces that hold one molecule together with another. So in addition, we're removing a lot of those slower moving water molecules, vapor molecules, which means that the net average kinetic energy of the water vapor, which warms it. So when we talk about condensation, it is sort of a warming process in that sort of vein. And when we talk about the process of going from liquid to gas or gas to liquid, and again, although we don't really talk too much about energy in this class, there is a certain amount of energy required to do those transitions. So again, this occurs at 100 degrees Celsius, and dead on at 100 degrees Celsius, you're basically have that both phases happening at the same time between liquid and gas. And there is what is known as the heat of vaporization, and is sometimes referred to as delta H of vaporization. And that's the energy required to do nothing more than take something from the liquid state to the gas state, or take it from the gas state to the liquid state. Again, for water, for example, this occurs at 100 degrees Celsius. There's no change in temperature where these transitions occur. And obviously, this transition occurs at the normal boiling point for a substance. This roughly translates to something like 2,260 joules per gram. And it is the same number regardless of which way you're going. So the delta H of vaporization would be 40.7 kilojoules per mole going in this direction. And the only difference is going from gas to liquid, it would be actually negative 40.7 kilojoules per mole. The negative here implies that it is exothermic. So the heat of vaporization is the energy that's required to do nothing more than take a substance from the liquid phase to the gas phase or vice versa, go from the gas phase back to the liquid phase at its normal boiling point. I think we'll see it a little bit later, but just in case we don't, there's also the delta H of fusion, and that is the energy needed to go from solid to liquid, or backwards, liquid to solid. So there is that transition again that occurs at the normal melting point or freezing point for a substance. So for example, for water, that would be 0 degrees Celsius as to where that would occur. And again, the delta H of fusion is for the transition of solid to liquid or liquid to solid. Again, in terms of the sign, same deal. It's endothermic going from solid to liquid. So that delta H of fusion would be a positive number, a negative number heading in the opposite direction, going from liquid back to solid. So in the same way that we sort of feel cold, for example, when we have water on us after a shower, after we get out of the pool or something like that, we also feel warm in a shower because usually when we take a shower, usually you have hot water. Hot water creates steam, and steam is going to want to go from the gas phase to the liquid phase, and that's going to be exothermic, which means all those water molecules that are in steam will start to go through the process of condensation, which means they're going to give off all that heat and energy. And with you standing there, you will pick up all that heat and energy from the steam that's coming off as it goes from gas back to liquid. And that's why we feel really warm. Again, if we take sort of a warm shower, and then obviously once you're done with your shower, right, you feel the opposite effect. Once you're done with your shower, you have water on your skin, as we were talking about in the previous slide, and then the rate of evaporation kicks off, and that's where we lose a lot of our body heat, and that's why we feel cold. So that's why we sort of feel both of those things. You know, when you do take something like a warm shower, you feel really warm because you got a very big rate of condensation occurring. It's giving off a lot of energy in the room that you're in, so you feel warm and good. But again, as soon as you kind of shut it off, you're left with a greater rate of evaporation, which again is why you will start to feel cold afterwards. Now, freezing and melting is the other transition, as we sort of alluded to, and we know, again, as we go from solid to liquid, that's the process of melting. Going backwards from liquid to solid, that's the process of freezing. Again, for water, that's 0 degrees Celsius, where that occurs. And again, that's the normal melting and freezing point. And by the way, at exactly 0 degrees Celsius, you also have both of those guys in equilibrium with each other. So you kind of have like ice crystals happening at that point. Now until you get a little bit above zero, that you actually get to liquid. Now until you get a little below zero, that you are back to solid. But exactly at 0 degrees, you basically have kind of like ice crystals, if you will. So you got a little bit of solid, you got a little bit of liquid happening. And again, this happens at the normal melting or freezing point for a substance, and melting and freezing occur at the same temperature. Again, really the only difference here is what is happening at that temperature. If you continue to put heat and energy in an endothermic type process, then the process of melting will continue as you go from solid to liquid. And if you take heat and energy out as you go the other way, it will go from liquid back to solid in that case. And to get water at 0 degrees to form ice, again, is going to need a exothermic process. So as it loses energy, the water, it no longer has enough energy really to move past each other, to kind of stay away from each other. And one of the weird features or different features that we see with water is because of all this hydrogen bonding that occurs, when it does get into the solid state, as they start to hydrogen bond with each other, what we end up getting is a lot of open spaces between the different water molecules. And these open spaces account for an interesting property of water that we don't usually see with substances, and that's density. And what we know about density of water in its solid state is it is less dense than water in its liquid state. And if you just think about density, right? Density is mass divided by volume, which means because we're creating all these big open spaces where I kind of colored in there between the different water molecules, our volume's kind of increasing. So it's kind of bloated, if you will. And that would mean, technically speaking, the bottom part here in our density would be a larger number, and then the density value would end up being smaller. As you can see in the liquid phase, they actually can get a little bit closer to each other. Again, they still have sufficient amount of energy to maintain being close to each other without sort of losing enough energy that they really do sort of spread apart like we see in the solid version. Endothermic, obviously going the other way, as we've talked about. Again, taking ice to liquid water, we'd have to put energy in, endothermic, and going the opposite way, again, being exothermic. The last sort of transition, and again, I sort of jumped the gun there on the slide, but this transition, again, going from solid to liquid or liquid back, that again is where we would use our delta H of fusion. And just for reference sake, it's something like 333 joules per gram for water. And if you compare that to the delta H of vaporization, which was about 2260 joules per gram for water, what we do see is what we know. The transition as we go from solid to liquid doesn't require as much energy as the transition as you go from liquid to gas. And if you just think about that logically, as we go from solid to liquid, which is what we got going on in these pictures, everybody is still relatively close to one another. They're near one another. But when we do the transition of going from liquid to gas, which would encompass this delta H of vaporization, everybody needs to 100% pretty much be like these guys. We'll just borrow these pictures. They pretty much are far apart from each other. They need to completely break apart from each other, break apart from those hydrogen bonds. And it takes a lot more energy to always sort of do that transition for a substance going from liquid to gas, because you're getting everybody completely far apart from each other, completely broken apart from each other, as opposed to when you typically go from solid to liquid, everybody's still relatively close to one another. And that brings us our last sort of transition here, which is when we go from solid directly to gas, or gas directly to solid, and we skip the liquid part. Yeah, so we skip the liquid sort of part of that transition. Heading from solid to gas, that is what is known as sublimation. And going from gas back to solid is what is known as deposition. Same idea in terms of energy. If we go from solid directly to gas, that's an endothermic process. Heat and energy has to be added or absorbed. As we go from gas back to solid, again, skipping liquid, that is an exothermic process. Heat and energy has to be given away. So really, if you sort of think about that, as we go from solid all the way to liquid, that encompasses our delta H of fusion for our basically solid to liquid transition, and our delta H of vaporization from our liquid to gas transition. And that means that to calculate something like the delta H of sublimation, which is the energy change to take something again directly from solid to gas, or backwards gas to solid without the liquid phase, you basically can add up those values. You can take the delta H of fusion plus the delta H of vaporization will get you basically all the way from solid to gas, skipping that liquid phase. So here is for water, what is known as the molar heat of fusion, and that's the delta H of fusion, 6.02 kilojoules. And again, in comparison to our heat of vaporization, like we just talked about, which is 40.6, it's about what we got there, 7-ish times the amount of energy is required to go from liquid to gas than it is to take something from solid to liquid. So again, a tremendous amount more energy required to do that. And that's our heating and cooling curve. And when we look at something like this, again, for example, if we're talking about water at 0 degrees Celsius here, really badly drawn straight line, that is where we would have our transition that occurs at that flat point from solid to liquid, or again, back from liquid to solid. And that's the part on that flat area of the curve where we would use our delta H of fusion. Again, if this is something like water, it would be 100 degrees, very badly drawn straight line there. And this is again where we would have our transition of liquid to gas, our gas back to liquid, and our delta H of vaporization that happens here. Now, again, something we don't talk about in this class, which you'll talk about in 1B or 200B or whatever they call it at this school, is that what happens as we go sort of upwards on this graph, for example, in each of these spots. And we'll just look here in the center. In the center, this is the same phase all the way through. This is liquid all the way through. So when we typically want to figure out how much energy is required to take something in the same phase, but change the temperature, that is when we typically will use Q equals ms delta T. This is what is known as the specific heat equation. And Q is heat or energy. M is mass. S is the specific heat capacity. And that's sort of a table value that you can find usually for different substances. And delta T is the change in temperature, final minus initial. And it's actually in degrees Celsius, one of the few things where we don't convert it to Kelvin. And that's about it. We're going to talk about that because you'll talk about that in 200B. There's a whole chapter that you'll go back and do, which I think is chapter 6 in our book. But in terms of energy, that's what we would use to sort of calculate when we basically we use specific heat, or this equation, when it's the same phase, but we change the temperature. And then the heat of fusion or the heat of vaporization, we use this when the temperature stays the same, but we change the phase. So you can keep that in mind for 200B when you get to it, I suppose. All right. So let's talk a little bit about phase diagrams. And phase diagrams are pretty much what the title implies. They are diagrams that show basically the different phases for a substance. And it shows the 3 different phases, which is solid, liquid, and gas. It also shows the 6 interconversions that happen between them. And when we talk about the 6 interconversions, we're talking about melting, freezing, evaporation, condensation, sublimation, all the ones we just talked about, and deposition. Yeah. So those are, again, the 6 sort of conversions that happens between them. The 3 phases, obviously, again, being solid, liquid, or gas. And what these phase diagrams basically show you is the combination of temperature and pressure that you need to get a substance in a particular phase. So what sort of temperature pressure combinations is necessary to, for example, get a substance in the solid state, or to get it in the liquid state, or to even get it into the gas state. As we'll see from one of these sort of diagrams in just a second, there's a part on the diagram which was referred to as the triple point. And the triple point's when you have all 3 phases in equilibrium. So it is the temperature pressure combination where that particular substance will exist in all 3 phases at once. So it'll be solid, liquid, and gas happening all at once. Water has an unusual sort of melting point line. And again, this is why under sort of normal situations, our ice is going to be less dense than our liquid water. Now, there's also a couple of other important areas on a phase diagram. One important area is what is known as the critical temperature, or TC. And that's the temperature above where there's basically no distinction between the liquid and the vapor phase. So that is basically a temperature and really kind of a temperature pressure combination where a substance basically will pretty much have properties of something that's in a liquid phase, but it will kind of flow more like a gas. So it has basically both of those properties sort of happening. And there's also a pressure where that occurs as well. And sometimes these two guys on a phase diagram are what are sometimes what is referred to as the critical point. And a critical point is the place where at that particular temperature and pressure, like I said, you get basically no distinction between, oh, this is a liquid or this is a gas. Again, you get a substance that basically has properties that fall on both sides. And usually when we get above that critical point on a sort of phase diagram, we get a fluid which is sometimes referred to as a supercritical fluid. And that's one where this fluid basically will have a density of a liquid, but it'll have the flow and properties associated with a gas. So on that curve, you'll basically hit a point in terms of pressure and temperature where as you go above that, you basically get what is referred to as a supercritical fluid. So let's take a look at a generic phase diagram. So typically speaking, going left to right here, between these lines, you have your solid, your liquid's usually in the middle, and then your gas phase is usually happening um, on the far right of this one. On the Y, we have the pressure. On the X there, we have the temperature. So again, this is going to give us our temperature pressure combinations that allow us to see these things. So since this is sort of the boundary between solid and liquid, and this line right here is between those two phases, that is sometimes referred to as the melting point curve or line. And as I go from solid to liquid and cross over that line, that's going to be melting occurring. Freezing would occur as I cross over the other way. As we go from liquid over here to gas over here, as we also cross that line as well, that's sometimes referred to as the vapor pressure curve. As we go from the liquid to the gas phase, that's vaporization occurring, condensation occurring, going the other way. Down here where the solid basically runs into the gas phase, right? Nothing in between, but going solid directly to gas. Again, that is the process of sublimation. Going the opposite way, that is the process of deposition. You can see where all three of these phases basically come together is right here at this point. And this point there is that triple point. So at that particular, if you went down, temperature, and you went over maybe straighter with a ruler. At that particular pressure and temperature, that is where for this particular substance, we would find this substance having all three phases basically occurring at once. Now, if you kind of come up here where liquid sort of blends into the gas phase up here, this right here is our critical point. And that also is, if you went down and over, that is your temperature pressure combination. This, if you went down, would be your very badly drawn straight line. That would be your critical temperature. And just to make sure I can't draw a straight line going this way, which I can't either. There we go. That would be your critical pressure going across there. Clearly with a ruler and much straighter than I butchered that drawing right there. You would want to do that. So that's your critical point. And if you go above that critical point, you're going to have, as you can see there from the graph, the liquid kind of flows into the gas. So again, here you have your supercritical fluid up there in the top right. And that again is something that basically will have some properties of a liquid, like density, for example, but will flow like a gas. So you do need to know where solid, liquid, and gas is on a phase diagram. You need to know where melting, freezing, vaporization, condensation, sublimation, and deposition occurs. And by the way, our normal melting point and boiling point would occur, we'll just randomly put it here, at 1 atmosphere, right? So sort of standard pressure is 1 atmosphere. Standard temperature is like 25 degrees Celsius. So if we want to know where our normal melting point would be, again, if this was 1 atmosphere, right about where that circle is, would be our normal melting point. And if we continued on again in a more straight fashion, that would be our normal boiling point where that would occur. And again, from those points, you could go down and figure out what temperature that would actually occur at as well. Any questions on the phase diagram here? All right, so a reminder that if you do have questions, make sure you ask them. But let's take a look at the phase diagram here for carbon dioxide. So we see a couple of things here. We do see our same things going left to right. That's our solid, that's our liquid, and that's our gas. And a reminder that as we go from solid to liquid here, wherever it went, solid to liquid, that is going to get us our melting, freezing going the other way. And then obviously way up here for carbon dioxide is our critical point. Again, above this temperature and pressure is where we would find that supercritical fluid. Now, if you know what carbon dioxide is, that is also what we sometimes refer to as dry ice. And dry ice, if you've ever seen it, ever used it, you might know that it goes directly from solid directly to gas and backwards. We don't have any liquid that occurs. And we can see why that is if we look at this diagram here for carbon dioxide. Again, under normal conditions, we are dealing with a pressure of 1 atmosphere, which is right here. And at 1 atmosphere, you can see that pretty much it's going to go directly from solid into the gas phase, right? And again, here at our normal temperature, somewhere in that area, we're not going to see that liquid phase basically come into play. Now, if you wanted to force carbon dioxide to actually go into the liquid phase, you could use this diagram to help you figure that out. What you would need to do is definitely get it to a pressure above 5.1. That's 5.1 here, I think. So you need to bump it up to a pressure above 5.1, and you would also need to hit it into a temperature, above minus 56.6. So clearly, again, we usually around, 1 atmosphere. So you would have to tremendously increase the pressure on the CO2 to get it to go into the liquid phase, and even more this way to get it into that liquid phase and actually see the liquid phase. But minimum, you would have to get it above this point here at the P3 and get it into that pressure and increase the temperature. And you technically would be able to perhaps see all 3 phases of CO2 actually happen and not just it going from solid to gas. But again, under normal conditions, in terms of pressure, we're way down here. And that's why, again, under normal conditions, we cross right on over into solid directly into gas, and we don't get into the liquid phase. Any questions on that? All right, so why don't you take a couple of a minute or so here, take a look at this diagram here for CO2. And what we're looking for is we want to know, based on this phase diagram and based on these temperature and pressure combinations that we have on the left, what phase would we expect the carbon dioxide to be in on each of those? So take a second and see what you come up with, and then we will talk about it. Okay, so let's take a look and see how we're doing. So the first one, we got 20 degrees Celsius and 72.9. So if we go over to our diagram, 20-ish is, in this region. And all the way up to 72.9 would take us, somewhere in this ballpark. And we can see in this ballpark here, we should be in the liquid phase in that case. Taking a look at the next one, we're at minus 56.7, which is right here on this dotted line. And we have an atmosphere of 5.1, which takes us right dead there. That again is our triple point. And remember, at our triple point, that is the point where we have all three phases in equilibrium. So we technically would have something that it's in the solid, liquid, and gas phase all happening at the same time. When we go to 10 degrees Celsius and 1 atmosphere, so again, 10 degrees, somewhere in this ballparkish. 1 atmosphere is coming across here. So that definitely is going to put us right about here. I'll box it. And we can see that that is, since this is the solid to the left, liquid to the middle, and this would be our gas phase over here. So we would expect it to be a gas in that case. Going to minus 78.5, which is at this little dotted line here, and to 1 atmosphere, which actually puts us right on that line. And that line is the line that separates both the solid and the gas phase, which means in this particular case, we would have both of those guys. So remember, if you find yourself on a phase diagram, say that's solid and liquid, right dead on the line, that means that you're at that transition between solid and liquid, and you would have both phases in equilibrium with each other. In this particular case, we're dead on the line between solid and gas. So again, we would have both of those phases in equilibrium with each other. And lastly, here we're at 50 degrees, which is past here, and 80 atmospheres, which is like up in this region. And that is past our critical point. Remember, when we get past the critical point, we would have a supercritical fluid. And again, a supercritical fluid is the fluid that basically will have the density like a liquid, but it will flow like a gas. Because again, you can see above that little critical point, there really is sort of no distinction, if you will, between the liquid and gas. They just kind of flow kind of right into each other. So you have properties that make both. Any questions on how to use a phase diagram to identify the different phases of a substance based on its pressure and temperature? Clearly, if you're given a phase diagram, you need to be able to answer some questions like this. Any questions on that there? Okay. And that's a ice skating blade. Nice picture. All right. Talk a little bit about water, just a little bit. We sort of touched upon some of this stuff. Obviously, water is important for life. It has a high thermal conductivity. And again, because of its ability to hydrogen bond, we do see some different properties than we see in normal substances. Again, one of the major differences is the density factor. Again, ice being the solid version of water will be less dense than liquid water. Again, why our ice cubes will float to the top of our drink and not sink. And that hydrogen bonding, again, is a bond, as we see here, between hydrogen and an electronegative atom like nitrogen, oxygen, or fluorine. And in terms of intermolecular forces, it is relatively kind of the strongest intermolecular forces. Remember, in terms of intermolecular forces, we have our hydrogen bonding, which is kind of the strongest. We have our dipole-dipole, which is also strong. And then again, the weakest out of all of those would be our dispersion forces. So kind of the strongest to the weakest, if you will. And remember that it is the intermolecular forces that basically affect things like melting point, boiling points, and those type of properties for substances. So the stronger the intermolecular force, the higher the things like boiling points are or melting points. And then obviously the weaker the intermolecular force, so things like dispersion forces in comparison to something like hydrogen bonding that has the ability to do that, would typically have a much lower boiling point our melting point because of that weak association. Again, it's really that intermolecular force, the force that holds those two molecules together. So the stronger that force is, the harder it is to separate. And that basically translates to a higher temperature in terms of boiling points and melting points. And that's also, again, why we sometimes will see certain things happen with water or things that have a lot of water in it. So, for example, I'm pretty sure we all probably try to cool down a beverage, maybe a soda can or something like that. And we put it in the freezer and then sort of forgot about it. And what happens is obviously the water or something in that beverage can go from the liquid phase to the solid phase. It's going to create all the big spacing out there. And obviously, what's going to end up right is the classic, can on the bottom that's kind of wobbly because it started to expand because those water molecules got larger and basically pushed out the can, right? And you kind of balance it and let it kind of teeter totter over, right? Now, some of the important properties of water is really important, especially for things, for example, in lakes and so forth. When we talk about the density of water and the density of any substance, it does change with temperature. So the greatest density that we see, for example, for liquid water is about 4 degrees Celsius. And even though we kind of randomly always say, hey, the density of water is 1 gram per milliliter, you should know, again, it does change with temperature. So, you could have water with a density of 0.9 something rather than 1. But at 4 degrees, it's much more dense than, say, at a lower temperature. And that's really important for what happens with water, how it freezes. So water, as you may know or may not know, water freezes actually from like the top down. It doesn't freeze from the bottom up, which is really good for things that are swimming around in the water, for example, like fish and so forth. If water did freeze from the bottom up, they would be like ice cubes at that point, right? But it actually freezes from the top down. And that's because what essentially happens is, as we'll see maybe in the next picture, is the water at like 4 degrees Celsius is more dense, so it kind of works its way down. The less dense water works its way up where it starts to freeze. And when it starts to freeze on top, it actually kind of insulates the bottom. And you still have your 4 degrees Celsius kind of liquid water underneath the surface. And that's why like lakes freeze and those type of things. And you can still cut a hole in it and go fishing, right? Because there's still fish swimming around underneath it. Or if you break through the ice on top, you'll be in liquid water again because it does freeze from the top down because of that. And that's what we see here. Again, the warmer water working its way down, the colder water works its way up, and it sort of freezes and makes this ice layer here. And then our good friend Melvin the fish, it's a good thing to know. You never know when that name will come up, Melvin the fish. Although he does look like he is in an ice cube right there, he's actually not. It's just some bad old cut and paste clip art, but he's actually swimming around. So again, this is good for things like fish and stuff like that because it allows obviously the water still to be liquid water underneath the surface. Again, because that more dense water goes to the bottom while the less dense goes to the top and basically will freeze. Any questions on water or anything like that? All right, so we're gonna talk a little bit about solids and sort of how some solids come together. And solids are rigid, which again means that you cannot transmit pressure in all directions. They have varying degrees of hardness. There's 2 types of solids. There's a crystalline solid, which has a very ordered arrangement of how all the particles, the atoms, everybody kind of comes together in the kind of solid phase. things like salts, minerals, gemstones, ionic compounds, obviously, when they do go into the solid state, they crystallize in this very ordered pattern, such an ordered pattern that it's very repeatable as well. An amorphous solid is a little bit different. They don't really exhibit these long range orderedness. They don't have a definite shape. So glass and so forth are examples of that. Now, when we talk about more the crystal lattice or crystal structure of a crystalline solid, which is basically what we're going to focus on here just a little bit, um, when it does cool slowly, the particles will really arrange themselves to maximize the attractive forces. So as we sort of talked about with intermolecular forces, which is basically, if you just get to the heart of the intermolecular forces, it's really positive guys attracted to negative guys. So the positive side of a molecule attracted to a negative side of the molecule. So when they do come together, they really do try to move around and arrange themselves in such a way that they really try to maximize the attractive forces. So the positive side of one molecule being next to the negative side of another. Why minimize those places where we have the negative side next to the negative or the positive next to the positive? No matter what you do, you're always going to have some of that happening. So there's no way to really kind of perfectly move everybody around that there's not sort of a positive guy near another positive guy, or at least in the same neighborhood. But they do try to move as much as they can to maximize that. So this arrangement of particles in a crystalline solid is what is sometimes referred to as a crystal lattice. And this is such an ordered arrangement of these atoms and molecules in the solid state that you could actually take a very small unit of that, which is what it says down here at the bottom. That is what is referred to as a unit cell. And a unit cell is really just a basically small portion of this big crystal structure where there is enough information in that little bitty piece of it that you basically could rebuild the entire structure just by repeating that same piece or that same unit cell over and over again. So when we look at something, for example, that are unit cells, it's important how we sort of pick the unit cell, for example. So if we think about our atoms or our molecules that are basically arranged here in three-dimensional space. And if we want to pick like a unit cell, for example, and we decide I'm going to pick a unit cell this way, I'm just going to pick this guy. That's a whole atom. That seems like a very good unit cell. So if I pick that as my unit cell, which is basically one whole atom or molecule in there, it's good for that one little piece, right? But it's not so good in helping us determine how everybody's put together. Do I know where the next little circle goes? Does it go underneath? Does it go to the left? Is it slightly off center? It doesn't really give us information about sort of its neighbors. So typically when we sort of select a unit cell, we wouldn't want to select one where we just take one whole atom or molecule with really no reference points to the other guys that are there. So for example, if we decide to take a unit cell where we take something like this, and if I take something like that, and I kind of take that little unit cell out, what I got is something that looks like this. And now, although I don't have the entire atom in that one unit cell, I have really more important information given to me. I have information about how to stack the next guy, because I know if I stack the next guy, say on top, I'll have another one that looks like this. And if I stack another one to the side, I'd have another one that looks like this. And if I stack one underneath and to the side, I'll have another one that looks like this. And what you could kind of see here is very quickly, I am now rebuilding basically my entire three-dimensional structure just based by taking those unit cells and putting them back together. So typically when we do take these unit cells, we take one that has information about an atom and then also some neighboring atoms and information, because that allows us really to rebuild the entire three-dimensional structure. As you can see here, this guy gives us information about 1, 2, 3, 4, and actually the entire atom that happens to be sitting in the middle of those 4 atoms. Information about all those guys. And then we can rebuild it. And you can see if you just keep repeating those, you will rebuild that three-dimensional structure. Again, here, same idea. We have information about all of our neighbors, how they're kind of connected to each other. We also have some other information. And again, it just allows you to rebuild that three-dimensional space. And you can do that because these crystalline structures are super repeatable. And so much so you could just basically take that small little unit. When we talk about unit cells, there's 7 different types of unit cells. And we're going to focus only on cubic unit cells. And cubic unit cells are nice because everybody's 90 degrees. It's kind of easy to sort of figure out what's going on with those. So we won't get into any of these other ones. We're just going to focus on sort of the few different types of cubic cells that we get. So when we talk about some things, how these unit cells come together, the number of particles that are in contact with these unit cells are sometimes referred to as coordination number. The higher the coordination number, sort of the stronger the attractive force is in that crystal structure. And we're not going to get too much into packing efficiency or anything like that, but you know, packing efficiency is basically how efficient it is when they all get together, able to sort of maneuver around to, again, maximize the attractive charges and minimize those repulsive type charges. So let's talk a little bit about cubic unit cells, which again are the only ones we're going to talk about. And cubic unit cells all have 90-degree angles. The lengths of the edges are equal to each other. And if a unit cell is made up of spherical particles, which is pretty much what we're going to deal with, at each of the corners of that sort of square, if you want to think about it, there's an eighth of an atom that's there. If we have something that's on the face of a cube, you'll have a half of an atom. And if we have a particle on the edge that is within the cube, you'll have a fourth of an atom. So for us, in terms of figuring out the volume of a cube, since we're only going to deal with cubic unit cells, basically to find the volume, which is an important thing for a calculation, you're going to take the length and you're going to cube it. So for all of ours, that essentially will be how we will find the volume. These are, whoops, come back. These are the 3 different types of cubic unit cells. There is the simple cubic, which is sometimes abbreviated with SC. And basically, for every simple cubic unit cell, you have 1 total atom. So that's an important relationship to know, that you have 1 atom per every simple cubic. And to find the length of the edge, it is 2 times r. So the length would equal 2 times r. R is the radius. Yeah, so that's important as well. When we have a body-centered cubic, which is sometimes abbreviated BCC, you have basically 2 whole atoms in every of those cubes that you get. And to calculate the length of the edge, it is 4 times r, which is the radius, divided by the square root of 3. Now, when we look at the last type, which is face-centered, that is also abbreviated sometimes FCC for face-centered, you actually end up with 4 total atoms that are there. And to calculate the edge length is 2 times the square root of 2 times r. That's actually not in, I'll do it like this. The r is actually not underneath the square root there. It's actually 2 to the square root of 2, 2 times the square root of 2 times r, which is the radius. You can see that the face-centered cubic gives you the greatest packing efficiency. Again, you got 4 atoms per square. You can really pack them in tight and get a lot of atoms basically in a very small part, as opposed to the worst sort of efficiency in terms of packing is here, where you basically only have 1 unit cell. So you do need to know this guy, and this guy, how many atoms there are per of those, and important for calculations will be these guys as well, how to actually calculate the edge length for each of those guys. All right, so let's take a look at each of these a little bit more in depth. Let's start with our, whoops, come back. We'll start with our simple cubic. And again, in the simple cubic, what we got going on is we basically have a square. And within that square, at each of the corners, we have an atom. And because it's at each of the corners, there's 8 corners in this kind of cube, if you will. 8 times 1/8 of an atom gives you the grand total of 1 atom per simple cubic. And again, 2 times R will give us our length for that guy. And here you can see if you put it all together, and it's cutting an atom in 1/8 at each of the corners of that atom there, basically in that cell. Now, for body center, it's a little bit different. When we look at it, we get an atom in each of the 8 corners, just like we had before. So that's going to give us 1 atom. But different as well, body centered, we get an entire atom sitting in the center of that cube, which gives us our extra one. And that means that for a body centered, we would start out with actually 2 atoms per cube. And the length of the edge there would be 4 times the radius divided by the square root of 3. Not sure what happened to the square root part of it here. We'll do that. And again, here you can see trapped in the middle of this guy, an entire atom. And again, these guys here, which purple on purple, not the best choice, is 1/8 of an atom in each of the corners. And the last one here is our face-centered. And in our face-centered, you can see what happens is we get our 1/8 of an atom in each of the corners, just like the other 2. So that's going to give us 1 atom. But we also have 6 atoms that are basically getting sliced right in half. And if you look at a cube, there is 1, 2, 3, 4, 5, 6 different sides to a cube. And since we're cutting 6 atoms in half, that's going to give us 3 more atoms for a grand total of 4 atoms involved here. And again, you can see here, it's a little bit easier to see. It is 2 times R times the square root of 2. And coordination number is 12. Again, you can see there's a lot of atoms touching each other, but here's a better picture. Those guys that are in the middle of the cube get basically sliced right in half, and you have a half atom that's sitting on the face of each of those sides. So let's take a look at what we do with something like this. We do a really long calculation just to get us, where we need to go. So for example, if we look at aluminum here, and it crystallizes in a FCC and has a radius of 143 picometers, we want to calculate the density in grams per cubic centimeters of aluminum. So here's where a couple of those things are really important that we saw on that table and that we kind of went through. The first important thing is it is FCC, which means it's face-centered. And from that table, what that tells us is FCC has 4 atoms per cube, and that's important. And it also tells us that, as we can see down there, the length is going to be 2 times R times the square root of 2. So ultimately, we want to get to grams, and ultimately, we want to get to cubic centimeters, right? And density is mass divided by volume, basically, is what we're looking at here. So we'll start with the top part, which is we want to get to grams of aluminum. So what we do know is I do have 4 atoms of aluminum. Now, if I have atoms and we want to get to grams, we probably need to get to moles. So that's where we can throw in our good friend Avogadro. We could use Avogadro's number here, 6.022 times 10 to the 23 atoms per mole of aluminum. And that gets me close to what I need for the grams part. That gets me to moles. And to get to grams now, I could use the molar mass from the periodic table, which is 26.98 grams per mole. So the moles will cancel, the atoms will cancel, and this will give me the grams of aluminum that I have in this unit cell. And this would be 4 times 2698 divided by Avogadro's number. And that's going to give me 1.79 times 10 to the minus 22 grams. That, believe it or not, is the top part of what I need. So basically, when you're doing these sort of calculations involving density of these guys, you're going to use the way that it crystallizes to basically figure out how many atoms there's going to be. And from that, you can use Avogadro's number and the molar mass, and that will get you to the grams part. But now we have kind of the cubic centimeters part that we got to get to, which is our volume. So remember that these are cubic unit cells. So as it says here, the volume is equal to the length cubed. Now, ultimately, I want to be in centimeters. Right now, the only unit I got is picometers. So what I'm going to do is calculate the length. So the length is going to equal 2 times r times the square root of 2. Again, because this is a face-centered, which is why we're using that formula. That's going to give me 2 times my picometers of 143 times the square root of 2. And that's going to give me something. Let's see. That's going to give me something like 404.47 picometers. Now, I can now take my length and put it into here and cube it, but I really want it in centimeters at this point, so everything will be kind of in the right unit. So before I do that, or you could do that right up front, I'm going to convert these picometers into centimeters. So we see that 1 picometer is equal 10 to the minus 12 meters. And in 1 meter, there's 100 centimeters, right? So there's 100 centimeters in a meter. And if we do that, we get 10 to the minus 12 times 100. We get give me some scientific notation perhaps. And we get something like 4.04 times 10 to the minus 6 centimeters. So here I'm just converting to centimeters to get everybody in the right units. So that's going to make everything a little bit easier perhaps at the end. And what I now can do is put it into my volume equation. And what we see is, again, the volume is length cubed. So the volume is now going to be 4.04 times 10 to the minus 6 centimeters. We're going to cube it. And that is what's really going to get us into our cubic centimeters, which is the units we're looking for. And I punch that in correctly, perhaps. We end up with 6.59 times 10 to the minus 17 cubic centimeters, which is actually the bottom part of what we need. So what is left to do at this point is actually now calculate the density. And just want to make sure I hit the right number there. I don't think I did. Let me just double check real quick. -6, and we want to cube it. Right, cubed, and that's why it's not right. I'm sorry, I put 6 instead of 8 here, right? So that should be 8. That looks better, I think. Let's see if that works better here. So I'll just double check here. I think I punched it wrong there. And that looks better. Okay, so this then should be, let me just get an eraser. Good thing they made erasers. Here we go. It helps if you look at your calculator right. All right. So up here should be an 8 to the -8. And then if you cube it at that point, you will get 6.63 times 10 to the -23. That looks better. Now we could actually calculate the density. So that's going to be 1.79 times 10 to the -22 grams divided by 6.63 times 10 to the -23 cubic centimeters. And you do all that just to get a number of 2.70 grams per cubic centimeter, which would be the density of aluminum. So to sort of reiterate this calculation here, we're going to use how many atoms that crystallize to go from atoms using Avogadro's number and the molar mass to get us to grams. We're going to use the length formula, depending on the unit cell, to get us to the length, which then we want to cube it. But somewhere along the way, you do need to convert usually into centimeters, so that before you cube it or even after you cube it, you need to get it to cubic centimeters, and then you're going to take the grams divided by the cubic centimeters. Any questions on any of that there, that calculation? All right, so why don't you try one and see how you do? Here's some information that will probably be helpful. I think that's the same one. Let's try this one here. All right, so why don't you give this a go and see what you come up with. I think all the information that you need here is on the screen. Here again, we're looking for the density in grams per cubic centimeter. So take a few minutes and see what you end up with, and then we will go over it and make sure everybody's on the same page. Okay, so let us take a look here and see how we're doing. So, although some of the stuff's given to you here, it probably won't be given to you. So, let's talk about important things, how we got to everything. So, important here is that it crystallizes body centered. So, remember, the body centered one is really the one that has the entire atom in the center, plus all those guys at the corners, which gave you your two atoms that happen for this guy. In addition, because it's body center, that means when we do the length of it, it is 4 times r divided by the square root of 3, which again is important as well. So again, we're looking for density here in grams per cubic centimeter. So that's where those two atoms are going to be really important for us. We're going to be able to use Avogadro's number and the molar mass to get to grams. So just like we did previously here, we're going to use Avogadro's number on the bottom, moles on top, and then using the molar mass from the periodic table, looks like it is 8547. And I'm going to try to punch this in without messing it up this time. Let's see. And trusty-ish calculator says 2.84, I hope, times 10 to the minus 22 grams. And again, that's going to be really the top part that we need for our density. Any questions on that part of the calculation there? We're going to now use really the other piece of information that's usually or a lot of times given to you, which is our radius here. And again, it's up to you. If you want, you could just, since you know you got to get to cubic centimeters or centimeters, you could just right off the bat, if you like, do the conversion. So if we take our, again, our picometers, we got 10 to the minus 12 meters in a picometer, and in a meter, there's 100 centimeters. So if we take all that to 47.5 times 10 to the minus 12 times 100, we end up with 2.48 times 10 to the minus 8 centimeters. And again, sometimes people like to do that conversion up front just to get it out of the way so it's in the right units. We now can take the length, which is 4 times the radius, divided by the square root of 3. And let's see here, square root of 3. We're going to take 4 times 2.48 to the minus 8 divided by square root of 3. That's going to give us 5.72 to the minus 8. And again, here, these are already in centimeters, so that's good. And again, because it's a cube, the volume will equal the length cubed. So we're going to take that number and cube it and hopefully end up better than I did last time. Again, we want to cube it. So we're going to take that number and cube it. Looks like perhaps 1.88 times 10 to the minus 22. And once we cube it, it becomes cubic centimeters. And if we now can calculate the density, as that's the bottom part that we need, we're going to take our grams. We're going to divide it by our cubic centimeters, which is our volume here. And it looks like we will end up with 1.51 grams per cubic centimeter as our density. Any questions on that there? So you do need to know these 3 cubic cells. So simple cubic, body centered, and face centered. Again, the important things to know for them, how many atoms each of them basically crystallize in, and how to calculate the length. And once you got that, you pretty much have everything you need to calculate something like the density. Sort of an alternative to this question would be if you're given the density and some other information, and maybe you need to figure out what the radius is or something like that, kind of going backwards. You can sometimes have questions like that. Any questions on any part of this calculation here? Okay. Now, that's good. I hope we got the same answer. I hope. Not bad with rounding, pretty close. Good deal. All right. Now that's close as packing spheres. Nobody really cares. This is an ionic structure, crystal structure. Again, as we sort of been talking about, you can see it's very ordered the way that they all kind of come together in three-dimensional space. The larger guys are chloride in this case. The smaller guys are sodium ions. And as we talked about before, when something becomes positively charged, it loses electrons. So obviously it's represented smaller here, while the chloride gained electrons, so it's larger. And again, they orient themselves in such a way to maximize that positive negative attraction and trying to keep as much distance as possible between positive guys and negative guys. And that is chapter 9. Yes. Any questions on that there, or what we talked about? Okay, a couple of things here. We'll stop lecturing here today on this. I did send a couple announcements out, so make sure that you do look at them. But just to summarize pretty much those announcements, the next exam will be 1 week from this Thursday, which is the 28th of May. We'll cover chapter, I think, 9, which we just finished, and we'll cover chapter 10 as well, which we should probably get through pretty much on Thursday. The new experiment for today, which is another gas experiment involving figuring out R, the gas constant. So you kind of know what the value should be, 0.08206 is what you're trying to figure out from the video is posted. So you should be able to look at that. Again, for that experiment, although it's labeled as a formal report, you don't have to do any type of typed lab report or anything like that. It's simply the pre-lab questions, the post-lab questions, fill out the data table and do the calculations, and that should be sufficient for that experiment. So that is due, I believe, next Friday, if I'm not mistaken. Coming this end of this week, you should have the formal lab report that's due. From the last gas experiment, where you're trying to figure out, I think, the molar mass of each of those, if I'm not mistaken. So that one is due coming up. And that will leave us really 2 more experiments. One's a boiling point 1, which has to do with colligative properties, which is what the lecture on Thursday will be about. So probably after the lecture on Thursday, and we cover sort of those colligative properties, that lab will be up, and then that will leave us 1 more lab, which is the kinetics lab, and we're down to 2 more chapters to go, which is chapter 10, which is the colligative properties, and then chapter 11, which is kinetics. So obviously we'll hit chapter 10 on Thursday. Next Tuesday we'll go through chapter 11, and then probably the following Tuesday as well if we need to finish it. And somewhere in there as well you'll have the last experiment, which I think was cut down to just the first part of the experiment. That's it, I think. So there's not much going on there. So those experiments are coming up. So exam 4, a week from Thursday, May 28th, and then 2 weeks from Thursday is the final, and then this show is over. Yes, so it'll be our last day there, which would be Thursday when the final will be. It will be comprehensive over the entire semester and all the chapters that we covered. So that's coming up as well. Any questions on any of the stuff coming up or anything about the class that you might have questions on? Okay, so like usual, I will take a little break, and somewhere around 7:15, 7:20, I will open up the lab session. And again, if you do have questions on any of these labs that you're currently working on, yeah, I recommend that you come by and ask questions. I'll be happy to answer them. So I'll hang out there for a bit to answer your questions. But I believe everything now should be up. The only two things still left again are the last two experiments, which again, we haven't really talked about the topics yet. So they haven't been posted because you might not know how to do them, obviously, until we get to there. So again, hopefully by this Thursday, we should get through to the next experiments, topics, and all that should hopefully work out okay. Any questions on anything? I did post up the grades that you got on your exam. Again, I can't release the exam just yet for a couple of reasons. I don't need to get into it, but hopefully by the end of the week, I should be able to release it so you can take a look at it. But I at least put up there your score so you can kind of see how you did on it. All right, if there's no other questions or anything like that, again, if you do have questions in terms of the lab or how to do something or lecture material or whatever questions that you may have, please feel free to come by the lab and I'll be happy to answer any of those questions. If not, you should definitely start working on those labs. Do not wait to the last minute because you have a lot of exams and finals coming up. So try to knock this stuff out and use your time wisely to work on these things. All right. So again, lab will start probably around 7:15ish, 7:20. Make sure you come through the lab invitation there if you are going to stop by and ask questions. If not, then I guess I will see you on Thursday.